Okay, so welcome back to lab. What I want to talk about now is measuring the mass of our string. So this is going to be a little hard to see. I've had to string an extension cord across the living room so that I can get this plugged in here, but what we have here is a digital balance. It has this plastic cover to protect the actual balance itself, but I've opened that up and you can see that there's a metal pan here. There's a display down here, which I am guessing you probably cannot see on your camera, but let me just describe what it's doing. So balance reads to 0.0 grams. So it can read to 1/10 of a gram. Alright, well, I've got this this fishing line here, which we have tended to use for string and mechanics experiments. And I've got a few pieces, but let me, here I have a pretty short piece. This is probably shorter than we might actually want to use. But let's just throw it on there and see what we get in terms of a mass. Okay, so I just put that little piece of string on here. So, and I got 0.2 grams. Now let's think about this, right? This is a balance that reads to 1/10 of a gram. So roughly speaking, there's going to be an uncertainty in that sort of last digit, right? So this is, if I had to make an estimate of this, right, this would be 0.2 plus or minus 0.1 grams. Now, that's a 50% uncertainty, right? And that's huge. That's not so great. So what's the answer here, right? What we probably want to do is to try to measure a long piece of string, and then, so if our string is ultimately a meter or a meter and a half long, we can, if we assume that the string has a uniform linear mass density, and we know how long like a 3 or 4 meter piece is, we can then go and try to estimate how long a 1 or 1.5 meter piece would be. So let's see if we can't do that. I'm going to just close the lid here for a sec. I have returned with a meter stick, and what we'll try to do is to measure out, let's see how, I don't know how much of this I have, but let's see if I can get at least like 3, maybe 4 meters worth of this stuff. So let's see, sort of get it to, see if I can sort of get this to play off the spool here. This is the sort of time when, like, if we were together, you would have a lab partner, and this would be so much easier. Okay, so that's 1 meter's worth. I've got my finger here. I'm going to keep playing this off, but I'm going to have to do that again because my finger slipped. Let's try that again. Okay, so okay, we have the end here. Okay, and we have 1 meter's worth there. Okay. Okay, so that's okay. And so that's 2 meters worth right here. There's still some more on the spool, so let me play off another meter or so. So that is 3 meters worth here, and one more time if I can. I guess I can. Okay. And see if I count. There we go. Right about there. So I'm gonna cut this and try not to stab myself. Come on. There we go. Okay. Okay, so we now have a piece of string that's about 4 meters long. If we were in the building, we have these like giant measuring tapes. That would be so much easier, but I don't have one at home. So let me just curl this up so that it doesn't go all over the place. La-di-da. So, yeah, probably most of you are better with strings and ropes and knots than I am, but it's doing our best here. Hope you're maybe enjoying the weather where you are. It's been warming up a little bit here in Ithaca. There are some flowers coming up in the yard. Okay, so here's my 4 meters worth of string. Let's put this on the balance and see what we get. Okay. Ah, that's better. Okay, so reading this, okay, so we have a length of string equals 4 meters. If you want to think about an uncertainty, I was eyeballing this with my fingers, so now I would say that there's probably an uncertainty of at least a centimeter or two in there, but this is a case where we're doing an estimate anyway, so I don't think we need to over concern ourselves with detailed uncertainty analysis. And then the mass of this 4 meter piece of string is 1.2 grams. So given that when I set this up, right, if I drag my stand here, so I know you can't see the entire thing on camera, but the end is on the floor. If I put a meter stick up here, right, the stand is roughly 1.3 meters tall. Stand is 1.3 tall. Again, like I said, I might be able to prop this up on maybe something low, but I'm not going to be able to get it up as high as I could if we were in our actual lab space. But I think you can, from this already, try to make an order of magnitude estimate of the mass of the length of string we're likely going to be able to use. So the other thing I want to measure here is sort of the spherical cowl radius of my hanging mass. Once again, here's my mass hanger. And when it's hanging, it's going to fall in this sort of funny oblique angle. But to get an order of magnitude estimate, let's just make things easier for ourselves by just holding it, assuming it falls kind of flat like this, which is going to end up overestimating the area anyway. So obviously this is not a sphere, I think you can see that. But it does sort of have a characteristic length scale, so something that would be roughly like the diameter if it were a sphere. If you had to ask me, what I would say is, well, let's get a rough estimate by just measuring sort of the total height of this thing, right, from the edge of this plastic all the way up to the top of this standard mass I've got here. So let's see what happens if I try that. So let me draw a picture. It kind of looks like a disc here, and it's got that roughly what the cross section of the bottom looks like. And let's go and try and measure that with a ruler here. So I have a ruler, and that's just about 45 millimeters, right? So 45 plus or minus 1 millimeter there. And that is, I think, all you need to be able to at least make an order of magnitude estimate of the air drag force. So now let's think about how to estimate the frictional torque due to these pulley bearings. Now what we really care about, right, is the kinetic friction, right? So what the frictional torque is when this pulley is actually spinning. It's not so easy to measure that, at least right now. So what we're actually going to do is, again, do a rough order of magnitude estimate by trying to estimate the static torque. You need to just start this thing moving. You've probably learned in Physics 117 that for like sliding friction, the coefficient of static friction mu sub s is always larger or equal to the coefficient of kinetic friction. We'll use that idea if we can get the static frictional torque. That should at least provide an upward bound on the kinetic frictional torque, and that should be a way to estimate, to at least put a conservative estimate of what's going on. Right. So how we can do this is, I have here a roll of blue painter's tape. I can try to attach some tape to the outer rim of the pulley. If I hang some tape from the edge of the pulley, there's going to be a torque in the negative direction. That's due to the gravitational force on this times my times the radius of my pulley. Right. So gravitational torque. So let me call that. So this is really my torque. Gravitational equals Rmg, right? But if we just do this so that our pulley just isn't quite rotating, right? And it's negative. So let me just actually put a minus sign here, right? Negative, right? If our pulley isn't rotating, right? So then the net torque is 0, and our net torque is going to come from friction in the bearing. So torque static friction plus the gravitational torque equaling 0. If I plug this in here, then I get torque static minus Rmg equals 0, which leads to the result. I wrote down that my static friction torque is roughly Rmg if I pick m just so that the mass is like just about this. Pick the mass of the stream so that this pulley is just beginning to move. Alright, so let's see what we need to be able to measure this. So I need the diameter of my pulley. I could try and get I think I might have calipers for this, but I can't find them this second. So let's just do an estimate with a ruler, and it's a little tricky since I want to get a diameter here. But if I eyeball this and try to read this without any parallax, so it looks like the diameter of the pulley diameter to R, that's about 5 centimeters. And let's just say that's 5.0 plus or minus. If I had I'd probably put a 2 millimeter uncertainty on here. So the diameter is about 5 centimeters, so that'll help. Let's think about the tape. Let me just try to cut this so that I get a clean piece here. Okay, so let's see if I can cut this without cutting myself. Okay. Alright, so let's see how long of a piece we need. So let me just start with a couple of inches. Okay, so I've got a piece, it's yay long. Let's see what happens if I attach this to my pulley. And yeah, it is definitely moving. So let's see, let's cut this down a little bit more. Okay. And I'm gonna try not to cut my own fingers here. Oh shoot, I've taken my notes. Okay, let's try this. Okay. I cut the tape shorter. Stick it there. Okay, and it's still moving, so that's still, I need to cut this even shorter. Okay. Okay, so this time, it depends on sort of where I have it. It's kind of right there. It's just like, okay, so this seems about the right length. Again, we're doing an order of magnitude estimate. I could probably try to refine this by like doing this a few more times, but just we're trying to get an estimate here. So let's just say that this is a piece of tape that represents the minimum mass we need. So let's see how long this is. So the tape, the length of tape is, there's some uncertainty here because the cut's not perfectly even, but let's just say that's about 35 millimeters. So L, length of the tape is 35 plus or minus 2 millimeters, right there. Now we need the mass of the tape, right? But it's going to be the same issue again if I just slap this onto the balance. It's going to be small. Let's see how big it is. I have my balance set up here. It has to power itself up. And if I put the tape on here, I've got 0.1 grams, so, oh, and it's actually reading 0 now, so that's actually not helpful. So let's zero this. Okay, so what we probably want to do is the same strategy we use to measure the mass of a string, which is, right, cut a long piece and then use ratios, assuming the tape also has a uniform density. So let's try that. I'm gonna move this out of the way. And let's do that. Let's just measure out maybe a meter or two of this. So tape's easier because it sticks. Have my meter stick here. And if I measure out, here's 1 meter, and I'll just wrap this around. Got a little extra at the edge, but I'm not going to worry about it. We'll just, so, okay, so let's just do, I'll do 3 meters, just so I don't, so I'll just wrap this around again. Okay, the tape didn't quite rip, so let's just go to here. There's some uncertainty in this. Okay, something like that. Something like that. And so if I go and cut this here. Okay, there we go. We peel the tape off the meter stick. We basically have two like end bits to worry about. So the 3 meters, just and 2 ends. Let's see, here we go. Okay. Okay, and just ball this up. So that's much better. Okay, so M long tape, our long tape has a mass of 14.2 grams that I'm reading right here, and we have the length. Right, it was 3 meters plus 2 of the edges. So if I go and measure that here, this meter stick looks like it's about about 8 millimeters. 8 millimeters thick this way, so plus 2 times 8 millimeters, so that's so 300 plus 1.6 centimeters, or 301.6 centimeters. So a little over 3 meters of tape had a mass of 14.2 grams. I think you can work out how much the mass of this length of tape was, and then that's our estimate of the frictional torque on the pulley.